Hi, welcome to this video looking at alkenes from the OCR A-level spec. I'm going to go through 4 different parts for today. We're going to look at properties and its kind of structure and the sigma and pi bonds in alkenes. We're going to look at stereoisomerism, specifically geometrical. Look at EZ, cis-trans isomerism. We'll look at addition reactions and the mechanism for them, and polymerization. So there's quite a bit to get through on this video. So first of all, properties. And what we have in alkenes, so we'll just do a very simple ethene, is we've got mainly sigma bonds. So all the CH's and one of the double bonds is a sigma, but the other one of the double bonds is a pi bond. And to show how that comes about, I'll draw a diagram where we put in all the sigma bonds. And that leaves each carbon, it's in group 4, so it's got 3 bonds, so 3 of its electrons are in covalent bonds. Its 4th one occupies a p orbital. So this excellent drawing is a p orbital. And what happens is, so we've got electron flying around here, electron flying around there, they overlap in the centre. So you get a bit of overlap between these 2 p orbitals above and below this sigma bond. And that leads to this occurring, the 2 electrons, one from this carbon, one from this carbon, moving above and below this electron being shared by both carbons then. And that is our pi bond. So if you ever have to draw a diagram to show how a pi bond forms, this is a diagram you show. But rather than draw this out each time with circle above and below, we just do it as a straight line to simplify it later on. This is pi bond's a lot weaker than the sigma bond, so breaks very easily, makes alkenes a bit more reactive than alkanes. It's also more electron dense, so it can induce dipoles. Right. Trigonal planar shape. Always interested in doing this. Now, trigonal planar, we've got here, if we just look at one of the carbons and how we draw it, we've got around this, we've got one bonded pair, a second bonded pair here, and this we take the double bond because it's held together as a single bonded pair as well. Really works a bit like a lone pair, it repels a little bit more, so this bond angle won't be exactly 120 degrees, this will be a bit large, maybe 124, so can't do the calculation in my head what this bond angle is, about 112, so a little bit smaller, but this is the trigonal planar shape. Essentially we're saying it's got 3 bonded pairs and 0 lone pairs, and so we get there a planar shape, and it's a triangle, if maybe a little bit skewed on this side. Stereoisomerism next. So previously we've looked at how sigma bonds can rotate. Now when we get a pi bond in, I'm going to draw the classic butene that you'll look at a lot when looking at stereoisomerism. We get our double bond like this, and now these bonds can't rotate. So these 2 CH3s, they're stuck on the same side. You wouldn't be able to rotate this round and get this CH3 to be on this side. Equally, this CH3 can't move to this side. So they're locked into position. So this is one version of butene, but another version could be made or formed where they are on opposite sides. But again, in this version, they wouldn't be able to rotate back to be in the same position as this one. So these two are different molecules. They can't be manipulated into this position. This one can't manipulate into this position. So to identify between the two, we use just a little prefix. We put the letter either E or Z. And my German's I'm not going to try to pronounce it. Entgegenhenken Zusammen. But E is where they're on opposite sides. And the way I remember it is if they're on opposite sides from each other, they are enemies. So this is E butene. And if they're on the same side, which then I pronounce the same side, with Z's, there's Z butene. Now this, and this example does actually fit for it, can also be known as cis and trans. Now, cis and trans is where two of the substituent groups are the same thing. So cis and trans we can use whenever really we see hydrogens. So trans, can kind of guess, is going to be on opposite sides. Kind of transport to get across to them is how I kind of remember it. So it could be called transbutene here. So this is cis, where they're on the same side. So either one of those works for this, and you'll see either one used as you go through the course. Cis and trans is really only when you've got two of the substituent groups are the same. So here we've got two hydrogens. Actually, the 2CH3 is the same as well. So it's cis twice. The Carningold prelog rules next is used to identify when we've got a whole mixture. And we can identify E and Z. So in this case, we are not going to have cis or trans. So let's put chlorine up there, a hydrogen, a fluorine, and a bromine. And then I can swap this around over on this side. If I just swap around the bromine and the fluorine, but keep this side the same, we've got E and Z isomers here. They're not structured the same, and we couldn't manipulate them to be the same. And what we do is we look at the carbon and we look at the atomic number of the first bonded atom. And we order the priority by weight. So chlorine 17, hydrogen 1. So chlorine gets my top priority on this side, hydrogen gets my second priority, so lower priority. On this side, same thing again, bromine much bigger than the fluorine. So our bromine is our higher priority. And so when we look at this now, we can see that the two higher priorities and the two lower priorities are on opposite sides to each other. So this is E. Bromo, 1 bromo, 1 fluoro, 2 chloro, ethene, by the looks of it. And that makes this Z. And we can show this out here. This would be 1 priority, 1 priority, 2 priority. We see the two 1s are on the same side here, and the two 2s are on the same side. So this will be the Z version of this particular molecule. Not cis and trans, because they're all different. Okay, addition reactions next. So go through the basic mechanism that we use for addition reactions. And what we'll have is our alkene. Now the alkene has an area of high electron density. So this can, if we have, I'll stick in black and use red for my lines. If we have a diatomic molecule that has no dipole, if it gets near that area of electron density, that can cause a dipole to occur. And so we get delta plus, delta minus, and then that lone pair, that weak pi bond breaks, and the electrons are donated into a bond with this part, this lower part, the electron deficient part of this diatomic molecule. So that's going to form a bond then with either one of these carbons. Then these electrons, because this now is got a bond elsewhere, go off and they go into the other part to form an ion. This leaves us with an intermediate where we have our X attached to one carbon, whatever the X may be, And then on the other carbon, we've now got a positive charge because it's lost. The one electron it donated into this double bond has gone into this bond with this X now. And we have up here X, which has become a negative ion. And it's got the 2 electrons it took from that bond. So this X and that lone pair specifically go like a bit of that plus. So they're going to be attracted to that carbon and form a bond with that carbon to create our X's on alternate carbons that were around the double bond. And yeah, and now an alkane with whatever that was attached. So that's the basic kind of reaction. Another thing you could have here, rather than having a diatomic molecule, so this could be at the moment H2 or Cl2, the common ones, is they could be a HCl or H2O already. And so we'll have a delta plus and a delta minus already there. It won't need to be induced, and then the same attack happens, the same mechanism happens from there. These will be attracted, especially the delta positive hydrogen, the delta positive hydrogen here, will be attracted to the lone pair as well, so it'll drag it closer to it, which is one of the reasons why it's more reactive. This electron deficient hydrogen in all this is an electrophile. It's going to accept that pair of electrons, and this is why this is known as electrophilic, because we're using an electrophile addition, because we're adding both of these parts of it on here to the compound. Let's just go through, because water's normally a bit trickier, just to kind of get an idea of. I'm going to do water. So we have our alkene. Now water, slightly different from all the others because we've got 3 atoms in this molecule, but the dipoles are still the same. They're just there, they didn't need to be induced by the double bond. So the pi bond breaks and goes to there, and this bond breaks and goes into the oxygen, which gives us the intermediate like this, and then the OH minus goes back into the carbon to now give us an alcohol. So everything's been added on. We used an electrophile to do it, so electrophilic addition. On bigger alkenes, when this reaction occurs, it's often we need to decide which side is one part going to go to, which side is the other part going to go to. And to work that out, we use Markovnikov's rule. Let's take, this time, propene, if we're acting it with HCl. So, this double bond's going to break. I'll put the hydrogens in very quickly. And it's going to, because it attacks that hydrogen. Now, that hydrogen could go to either this carbon or this carbon. And most of the time, not all of the time, but most of the time, it's going to prefer to go to this carbon because it's got more hydrogens on it. So we look at which carbon's got the most hydrogens on, that is going to take the hydrogen from this interaction. Also, this carbocation is more stable. So this is more stable than if the positive charge was on the end carbon. So then the Cl minus comes in and goes onto that carbon. So we get 2 products from this being the major product where the Cl goes onto the centre. So chloropropane, 2 chloropropane, but 1 chloropropane can exist as well. It will get formed from this reaction as well, just not in a higher volume as 2 chloropropane. Polymers. you're most likely going to get given an alkene. And if we take an alkene, I'll take propene again. Let's draw it properly with its trigonal planar shape. And get told, well, if you heat this up and pressurize it, lots of propenes all together, you get a polymer. And what happens is the pi bond breaks, and that breaks on all the propenes all together, and so they all now want to get stable by forming new bonds, and so they all connect together. So we have our C to C bond, still the sigma bond size, but the pi bond breaks, and that forms a sigma bond with the next carbon along. And obviously on this side, we've got a carbon here that's going to form a sigma bond with there. But just because it's constantly repeating, to shorthand it, we're going to put brackets around it with the lines going through the brackets to say this is going to continue on. And up here, we've got this CH3 group, below a H, up here a H, and there a H. And now what often happens, because to show there's lots and lots of them, we say there are N numbers of this one, and there are N numbers of this repeat unit. So this is the monomer, and this is the polymer. And you will get either asked, here's the monomer, draw the polymer, or here's the polymer, draw the monomer. The other thing with this is just to look at the waste products and what we do with it. And we process it in lots of different ways, these polymers. After we use them, we can combust them to get energy production. We can use as organic feedstock. We can use it to create plastics and other organic chemicals. Or we can use it to remove toxic waste products. But there's some a lot of the polymers don't biodegrade, so they become a bit of a problem. They last for years and years and years and years. So there are now big pushes to make polymers that do biodegrade. So if they ever get left out anywhere, they'll break down and that won't pollute the environment as much. That is alkene chemistry.